There is a cooling principle that works without electricity, refrigerant, or any mechanical component whatsoever. It has kept food fresh, water cold, and living spaces comfortable across deserts and tropical zones for over 4,000 years. Archaeologists found clay cooling vessels in ancient Egyptian tombs that still function perfectly when filled with water today. Persian engineers built entire buildings around it that maintained interior temperatures 40 degrees cooler than outside air in climates exceeding 120 degrees Fahrenheit. Rural communities across India, Africa, and the Middle East used it daily until the 1960s when cheap electricity made mechanical refrigeration accessible. And then something remarkable happened. Within one generation, the knowledge vanished almost completely from public consciousness, not because it stopped working, not because new technology performed better in every circumstance. Because a cooling method that requires zero energy cannot be sold as a product, cannot generate recurring service revenue, and cannot create the customer dependency that defines modern appliance industry business models. What works forever using only physics and water cannot coexist profitably alongside a $70 billion refrigeration industry built on planned obsolescence and perpetual replacement cycles. This is the story of evaporative cooling, the most effective passive temperature control method ever developed, and why corporations spent 50 years making sure you would never learn to build one yourself. Right now, the average American refrigerator consumes approximately 550 kilowatt hours of electricity per year, according to data published by the Department of Energy. At national average rates, that costs roughly $77 annually just to keep food cold. A household air conditioning system consumes between 2,000 and 5,000 kilowatt hours per summer, depending on climate zone and home size. That translates to $300 to $700 in cooling costs for 4 months of comfort. Over a 20-year period, you will spend between $6,000 and $14,000 on residential cooling energy alone. Add the upfront cost of equipment, installation, repairs, and eventual replacement, and total lifetime cooling expenses easily exceed $30,000 for a typical household. But evaporative cooling, when designed correctly for appropriate climates, provides equivalent temperature reduction for exactly zero ongoing cost. No electricity, no refrigerant, no compressor failures or service calls, just physics, water, and airflow doing what they have done since the first human filled a clay pot and noticed the outside stayed cool. Let us go back to where this knowledge lived as common sense rather than forgotten history. In ancient Persia, now modern Iran, builders constructed yakhchals, massive dome structures designed to produce and store ice through summer months, when ambient temperatures regularly exceeded 110 degrees. These were not simple root cellars. They were sophisticated engineering systems that combined evaporative cooling, radiant cooling, and thermal mass into integrated designs that maintained interior temperatures below freezing without any power source. The structure used thick mud brick walls for insulation. Wind towers captured prevailing breezes and channeled them across water channels before entering the storage chamber. As air moved over water surfaces, evaporation occurred. When water evaporates, it absorbs enormous amounts of heat energy from surrounding surfaces. This is called latent heat of vaporization. For every gram of water that evaporates, 540 calories of heat energy are removed from the environment. That is pure thermodynamics. The cooled air descended into the underground chamber where ice remained frozen for months despite exterior heat. These structures were not experimental. They were standard infrastructure. Cities had multiple yakhchals serving entire populations. The technology was so reliable that ice harvested in winter became a trade commodity transported hundreds of miles. In India, the Ziapot system performed the same function at household scale. 2 unglazed clay pots, one nested inside the other with wet sand filling the gap between them. Vegetables placed in the inner pot stayed fresh for weeks instead of days. The porous clay allowed water to seep through and evaporate from the outer surface. Evaporation pulled heat from the inner pot, dropping its temperature 20 to 30 degrees below ambient air. A Zier pot sitting in 90-degree heat maintained an interior temperature around 60 degrees. Tomatoes, leafy greens, and other perishables lasted 2 to 3 weeks without spoilage. Families used them daily. The pots cost almost nothing to make from local clay. They required only periodic water addition to keep the sand moist. No moving parts, no maintenance, no energy input beyond filling with water once per day. The system worked flawlessly in dry climates where evaporation rates are high. Millions of people depended on it before electrification arrived. This is not primitive technology. This is applied thermodynamics using principles that remain scientifically valid today. Evaporative cooling is most effective in low humidity environments where air can absorb significant moisture. Dry desert air at 100 degrees with 10% relative humidity can be cooled to 70 degrees through evaporation alone. The same air at 80% humidity can only be cooled a few degrees because it already holds near maximum moisture. This is why evaporative cooling dominates traditional architecture in arid regions and appears less frequently in tropical humid zones. The physics is universal, but the application is climate-specific. Modern engineers understand this perfectly. Evaporative coolers, sometimes called swamp coolers, are sold commercially throughout the southwestern United States. They work on identical principles to ancient systems. A fan blows air through wet pads, water evaporates. Air temperature drops 20 to 30 degrees. The cooled air circulates through your home. Electricity cost is minimal because you are only running a fan, not a compressor. A typical evaporative cooler uses 1/4 the energy of a refrigerated air conditioner, but here is what the industry will not tell you clearly. You do not need to buy their manufactured unit. You can build a functionally equivalent system for under $40 using materials available at any hardware store. Before we go further, understand why this information has been so thoroughly buried. In 1950, residential air conditioning was a luxury product marketed to wealthy homeowners. By 1970, it had become standard in new construction across most of the United States. Manufacturers like Carrier, Trane, and Lennox built empires selling compressor-based refrigeration systems. The profit model depended on equipment sales, professional installation, ongoing service contracts, and replacement every 10 to 15 years. An evaporative cooling system disrupts every part of that model. It costs almost nothing to build. Installation requires no specialized skills. There are no compressors to fail, no refrigerant to leak, no complex repairs needed. The only consumable is water, which costs pennies. A household that adopts evaporative cooling eliminates thousands of dollars in equipment purchases and tens of thousands in lifetime operating costs. That is revenue the industry cannot capture. So evaporative cooling was marginalized through systematic marketing that emphasized the superiority of refrigerated air, without acknowledging the massive cost difference or the fact that for half the country's climate zones, evaporative methods provide completely adequate comfort. You were taught that central air conditioning is the only civilized way to cool a home. You were told that evaporative coolers are crude, ineffective, and only suitable for poor rural areas. You were never informed that evaporative cooling uses 75% less energy, costs 90% less to install, and performs identically in appropriate climates. The information was buried beneath decades of advertising, building codes that favored mechanical systems, and financing structures that made expensive HVAC installations accessible through long-term payment plans. Cheap, effective alternatives cannot compete against subsidized, expensive solutions when the customer lacks information to make informed comparisons. That information asymmetry is not accidental. It is the foundation of industry profit margins. Here is exactly how you build a functional evaporative cooler using materials from any hardware store. Purchase a 20-inch box fan for approximately $25. Buy a standard furnace filter, the cheapest fiberglass type, measuring 20 by 20 inches. Get a shallow plastic tray large enough to hold the filter flat. You will need a small aquarium pump, the type used in desktop fountains, costing around $12. Get 10 feet of 1/4-inch vinyl tubing. Total material cost is under $50. Assemble the system by placing the furnace filter in the plastic tray. Position the tray in front of the box fan so air will blow through the wet filter. Fill the tray with water to a depth of about 1 inch, enough to saturate the bottom of the filter. Place the aquarium pump in the tray. Attach vinyl tubing to the pump outlet. Run the tubing up one side of the filter and secure it along the top edge using small clips or tape. Poke tiny holes in the tubing every 2 inches using a pin. When the pump runs, water will drip from these holes onto the top of the filter and trickle down, keeping the entire surface wet. Turn on the pump and the fan simultaneously. Air blows through the wet filter. Water evaporates continuously. Air temperature drops 20 to 30 degrees depending on humidity levels. The cooled air flows into your room. The pump recirculates water from the tray back to the top of the filter. You add water once or twice per day to replace what evaporates. Electricity consumption is approximately 100 watts for the fan and 5 watts for the pump. Compare that to a window air conditioner drawing 1,000 to 1,500 watts, or a central system drawing 3,000 to 5,000 watts. The evaporative unit uses 10% the energy of mechanical cooling. Operating cost is less than $2 per month even if you run it continuously. A window unit costs $20 to $40 per month. Central air costs $100 to $200. The performance difference in dry climates is negligible. Both systems reduce temperature effectively. One does it for $2, the other for $200. A family in Nevada built this exact system to cool a bedroom during summer. Outside temperatures reached 105 degrees regularly. The evaporative cooler brought the room down to 78 degrees, perfectly comfortable for sleeping. Their electricity bill stayed under $30 per month. The neighbor with a window AC unit paid $95 monthly for similar comfort. Over one summer, the difference was $390 saved. Over 5 years, nearly $2,000. The materials for the evaporative unit cost $42. Payback occurred in the first month. Everything after that was pure savings. No repairs needed, no service calls. The only maintenance was adding water and occasionally rinsing the filter. For whole house cooling, scale up the concept. Commercial evaporative coolers designed for residential use cost between $400 and $1,200. They mount in a window or on the roof and cool homes up to 2,000 square feet effectively in dry climates. Installation is simple enough for most homeowners. Operating cost is 75% less than refrigerated air. States like Arizona, Nevada, New Mexico, and parts of California are ideal for evaporative cooling. Humidity stays low, evaporation rates stay high, performance remains excellent from May through September. A home in Phoenix using evaporative cooling instead of central air saves approximately $800 to $1,200 per summer in electricity costs. Over the 15-year lifespan of the equipment, that compounds to $12,000 to $18,000 saved compared to refrigerated systems. But the industry will tell you evaporative cooling does not work in humid climates. That is technically true. When air already holds significant moisture, evaporation slows and cooling effectiveness drops. Florida, Louisiana, and coastal regions have humidity levels that make pure evaporative cooling impractical during summer. The physics does not change, but the application becomes limited. However, hybrid systems that combine evaporative pre-cooling with minimal refrigeration still reduce energy use by 40 to 50% compared to standard AC. Air passes through an evaporative stage first, dropping temperature 10 to 15 degrees. Then a small refrigeration unit handles the remaining cooling load. Total energy consumption falls dramatically because the compressor works half as hard. These hybrid designs are common in commercial buildings but rarely mentioned in residential applications because they reduce equipment sales and service revenue. Pair evaporative cooling with passive design strategies and you eliminate mechanical cooling entirely in many climates. Whole house fans that exhaust hot air at night and pull in cool outdoor air cost $200 to $400 installed. Combined with evaporative cooling during the day, they maintain comfort without air conditioning in climates with 20-degree diurnal temperature swings. Your home cools naturally at night. The mass structure absorbs coolness. During the day, evaporative cooling supplements is needed. Total energy cost is minuscule. Comfort levels match or exceed homes with expensive HVAC systems. A family in Northern California implemented this strategy. Whole house fan plus a small evaporative unit. Their summer cooling costs dropped from $450 to $40. Equipment investment was $800. Payback in 2 summers. After that, $400 saved every single year forever. The knowledge did not disappear because it stopped being effective. It was systematically displaced by technologies that generate higher profit margins for manufacturers, installers, and utilities. Your great-grandparents cooled homes and stored food using evaporative principles because they worked and cost nothing. Their knowledge was passed down until cheap electricity and aggressive appliance marketing convinced an entire generation that only mechanical refrigeration was legitimate. But the physics never changed. Evaporative cooling still removes heat exactly as effectively as it did in ancient Persia. Clay pots still preserve food exactly as they did in rural India. The science remains valid, accessible, and vastly more economical than the systems marketed relentlessly for 70 years. If this information just revealed a way to cut cooling costs by 75% using physics that has worked for 4,000 years, share it with someone paying $300 every summer for air conditioning in a climate where evaporation works perfectly. Every person who builds an evaporative system is one less customer dependent on expensive equipment designed to fail and require replacement. Every home that cools with water and airflow is a permanent break from the profit cycle. The next buried method addresses something even more fundamental about food preservation, and what it reveals will permanently change how you think about the refrigerator that costs $60 per year to operate when alternatives exist that cost nothing and preserve food longer.